Alright, now we're going to talk about extensions of the fundamental theorem of calculus. So we're going to be practicing this tomorrow. When we talk about fundamental theorem of calculus as accumulation, integrate removes the rate. And so if we're talking about a rate of change, if we're integrating our rate of change, such as in population, rate of change in population, that means we're going to get the total population between that was added between B and A. So it doesn't really matter what the starting rate is. We could have a population of, like, in 1,000 years ago, the population was less than 1 billion. If we want to talk about what is a change in population from 1,000 years ago, which started off as, I don't know, I'm just going to use a random number, let's say 500 million. And then over 1,000 years, the population has grown 6.5 billion, then that rate of change of growth of that 6.5 billion, that's going to be the capital P of B minus capital P of A. So that's the total rate of change. But what I mean that is the population, not the rate, but the population change over that total time. You could also talk about a change in amount. So if you want to talk about, maybe an example is like a change of added water. So if we're talking about a rate of change from like water is going into a pool, which seems to be a pretty popular problem on the test. When they're talking about capital R of B and capital R of A, we're talking about what is the height difference, or maybe even like what is the volume difference of the water at time A and time B. They also used sand. They've used traffic. I think they used a tea kettle once with boiling water for tea. And so these are just various changes in rates. So you also can use the fundamental theorem of calculus to find the terminal value, meaning like the ending value, the final value, the final position. So integrate to find the end. So if you have a position function, you want to find where your ending value is. What you can do is you can do your start, S of A is your starting spot, and then add it to the change in your distance. And so that'll give your position at a certain time B. And I'll give a couple examples of that. If you want to talk about your total amount of water, so when we talk about that rate of change, so if I know that, for example, I'll go back to my population thing. And so if we're saying, okay, I want to know what's the total population, I know I started off with 500, the R of A will be the population 1,000 years ago. That was at 500,000. And I know that at a growth of 6.5 billion, and so my current population date is 7 billion. Okay, that's what that means for that total amount. It gives you everything from the starting plus that change over time. Finally, they talk about finding as a constant with a known area, integrate to find the unknown. And so what you can use is you can use your known area, which is A, and then go back and solve for a K. And I have several examples of these so you can see. Number one, if the antiderivative, if the antiderivative from -2 to 2 of x to the 7th plus k, here's our unknown. Dx is equal to 16, then, sorry, this is supposed to be k. K is equal to what? So let's go ahead and take the antiderivative, and so that gives me x to the 8th divided by 8 plus kx, and these things are evaluated from -2 to 2. And so let me go ahead and plug in. So I have 2 to the 8th over 8 plus k times 2 and I'm going to subtract that from -2 to the 8th over 8 plus k times -2. Alright, so let's drop our parentheses. So 2 to the 8th plus 2k minus -2 to the 8th over 8 And so instead of writing, this is essentially saying negative 2k, a negative times the negative is a positive. When I have the value of these two, even though this guy says it's negative, because my exponent is positive, these guys are going to cancel each other out. The value is going to be the same, and so I have the positive version and negative version. They'll cancel each other out. And so I'm left with 2k plus 2k, and they told me that's equal to 16, so I have 4k is equal to 16. That means k has to be 4. Number 2, a particle moves along the y-axis such that the velocity is equal to t sine of t squared for t is greater than or equal to 0, given that s of t is the position of the particle, and that the starting point, I know a starting point because my x-coordinate, or my t-coordinate, excuse me, is 0. Find s of 2. So s of 2 is going to equal s of 0. That's my starting point. Plus the antiderivative, the change, so the change, the total change of the position from 0 to 2. So that's going to be the total change from 0 to 2 of my position. That's going to give me my antiderivative. And so I can go ahead and write my t sine of t squared dt. So s of 2 is equal to my starting spot, which is 3, s of 0, plus the antiderivative of this guy. And so go ahead and use your calculator. Alright, go ahead and use your calculator. You can use Math 9 or you can use that graphing feature that I showed you. And so when you take the antiderivative of the red, we're going to get 3 plus, and go ahead and just truncate it, 0.826. If you want to round, you can round. And so now I'm just going to add those two together. And so my final position at s of 2, so this was my starting position. I moved, this is my total movement between 0 and 2. And so 0.826, and so now my current position at s of 2 is 3.826. Finally, number 3, metal of length 8 centimeters is heated at one end. The table below gives selected values of the temperature T of X, gives the temperatures in Celsius of the wire X from the heated end. Find the antiderivative from 0 to 8 of T prime of x dx and indicate units of measure, explaining the meaning of the temperature of the wire. And so this right here is our antiderivative. And so if we're talking about the antiderivative from 0 to 8 of t prime, of x dx, then we're talking about the total change in temperature, capital T minus of 8 minus T of 0. Well, T of 8 is 55. T of 0 is 100. So we're talking about negative 45 degrees Celsius. And so let's answer in terms of the problem. And so we're talking about metal of length 8 centimeters is heated at one end. Well, at x equals 0, that's where it's currently being heated. This is the other end. And so we're talking about the wire cools. So I know it cools because it's negative. And so the wire is cooling from, we'll say, cools 45 degrees Celsius, 8, centimeters from the heated end. There we go.